Well, thank you, Emmanuel, for this introduction. So, yeah, I'm Jérôme Kieffer from the European synchrotron, and I will speak to you today about PyFAI, which is a Python library for high-performance azimuthal integration using GPUs. So we had already a talk this morning about GPU programming, and Yanis will present what he did really on the hardcore part. So well, I know everybody doesn't do X-ray diffraction, but I'd like to make this talk usable for that gives you some hints, even if you're not doing X-ray stuff. So I will start by introducing what is X-ray diffraction, and then we will go more on the computing side that may be interesting for most of you. We'll show some benchmark, and I will expose the Pythonic interface at the very end. So X-rays are light, like this laser pointer, except that the wavelength is much shorter. That allows it to enter the matter. And if your matter is crystalline, you get scattering. That means that the X-ray are reflected on the crystal. And I don't know if on this image maybe it's better to see. You can see small spots, and each spot corresponds to rows of atoms you have in your crystal. And the position here depends really on the spacing between these layers of atom. And it was formalized a century ago by Bragg, father and son, as Bragg's law. And in this talk, we will be more interested into powder. That means we have a lot of powder that are all made of small crystals, and small crystal will give us, well, rings. So we will analyze rings on images. Powder diffraction is quite interesting for many people. It allows us to identify chemicals, do mapping, analyze the crystallinity, measure lattice parameter, measure crystal structure, assess phase transition, measure crystal size, and so on. It has well, that's for powder diffraction. You can also apply exactly the same methodology to small angle scattering that allows us to study protein folding, particle shapes, colloids, and things like that. And the first step is to record an image that looks like that, and to transform it into the radial profile that you can see here, using PyFAI or one of the numerous software that are available. So how would you do that in Python? The idea is to extract a corona you have here. So this corona is known by its inner radius and outer radius. We calculate here, and we do the mask using we keep all pixels that have a radius greater than the minimum and lower than the maximum. We extract all values of the image according to this mask, and we take the mean. Great, it works. 40 seconds. Yeah, well, we have a loop in Python. The first trick is to take this mean and to separate this mean into two parts. So the mean is the sum divided by the number of elements. The sum can be calculated like that. The number of elements is the sum of what is in the mask. And those can be vectorized using intensity-weighted histogram and unweighted histograms. So this whole small snippet of code can be redone in 3 lines containing 2 histograms. So 2 call to histogram, 1 unweighted, 1 weighted, and we divide the weighted one by the unweighted one, and we have already a factor 15 speedup. That's not bad. The problem is that, well, all other programs are at the same speed. And yeah, it's a problem of speed because yeah, right now ESRF and many other light sources around the world are going a major upgrade program, and at ESRF we are expecting a factor 50 increase in brightness, and yeah, our program will have to follow. So that's one problem. The second problem comes on the detector side, but it's really related to the brighter source. Is that we have new detectors that are arriving this year, at the end of this year, and that will produce 3,000 frames per second, and each frame is between 1 and 16 megapixels. So very, very high data rate, and our program should be able to cope with this. So there's a gap between what we can do with NumPy really easily and what is expected by scientists. In addition to that, they want a better precision. We are offering a 1 pixel precision. They like us to take care of the corner of the pixel and split pixel. And they like to be able to work at 3,000 frames per second. Well, as I said, we have also programs in Fortran, we have programs in C. They are about a fraction of a second, but they don't reach the 3,000 frames per second, and we'll see how we try to go in that direction. So the first idea is to go to Cython. We go to compile code. It's straightforward, single-threaded. We can do the histogram. One nice thing is that when we have our array, when we call numpy.histogram, we are loading it a first time. We do a first histogram. We're loading it a second time. We're doing the second histogram. Our data set is larger than the CPU cache. Here, we can do both histograms at the same time, the weighted and the unweighted one. And we have a factor 5 or 6 in speed up because we have a better use of the cache. So Cython is great for that. Then we go parallel. Bam. Doesn't work. Yeah. Well, it works, but it gives wrong results, which is yeah. So yeah, when you're doing histograms, you may have 2 adjacent pixels that are treated by 2 different threads, and they are writing at the same place. So you have a write conflict, and without protecting this by an atomic operation, you're doomed. So, well, it took us some time, and we find a trick, but it's just a trick. So the idea is to have each thread doing its own histogram, and then we merge all histograms together. Yeah, well, but it costs some time to do the merging, and it also costs a lot of memory, because if you have 2 threads, it's okay. If you have 16 threads, it's still okay. But what if you have 256 threads? Do you have 256 times the memory available? So, well, we have the figures here, and yeah, going from 1 to 2 threads, it's great, but then it's not more that good. And we have this problem that the scientist wants pixel splitting. So, Yanis?
Hi, everyone. So I'm going to cut pixel splitting. So there is the case that many detectors today have a limited resolution, and pictures obtained by those detectors usually give us great statistical error.
This is in the bird.
They give us great statistical error, especially in the case where we have like a great number of bins. That will means that many beams remain unpopulated or sparsely populated. One way to go around this is to consider the pixel not as a point in space, but actually as a polygon. And when it spans over more than 1 bin, we split the contribution to both bins. That's what we call pixel splitting. We devised 2 pixel splitting schemes. The first one initially was based on the bounding box, which is in principle an abstraction of the pixel by a rectangular box that circumscribes the pixel and has its sides parallel to our space's axis. Instead now of using the area of the pixel segment to calculate the contribution, we use the area of the bounding box segment. This makes the calculation much easier and gives you good performance. But on the other hand, because we are overestimating the size of the pixel, we might have a bit of blurring in the final results. To solve this issue, we introduced the full pixel splitting, where no abstraction takes place, and we take the exact contribution of the pixel segment area. But this it's more complicated and results with more slow code. No, highway. Okay, this is a GPU. To achieve faster speeds, one solution was to move to many core architectures like GPUs and many core accelerators like Xeon Phi from Intel, which they allocate more silicon in computation instead of memory prefetching and cache coherency and stuff like that. But to fully utilize probably such architectures, we need to take some considerations into mind. And this can be done with the OpenCL standard, which is made for exactly that reason. The kernels, which are in principle the functions of OpenCL, are written in a C-like language. There is also a C API, which is the standard from the consortium, but we choose to use the PyOpenCL module that makes it much easier to program with OpenCL by giving lots of shortcuts and facilitates coding. So, but as we said before, our algorithm requires double precision floating operations, which are not supported by the standard. There is a way to hack them into the code by using complex and swap, but as you might guess, the performance won't be very, very good. So what is left is to actually change the algorithm. Parallel algorithms can be decomposed into these primitives here, which is map operations, where we apply a function on the same function on all elements of an array. A scatter operations where multiple outputs are set into an input, and gather operations where a single output is passed at multiple inputs. A reduction which returns one element out of a big array. A scan where we apply an operation to like cumulative sum to get a perspective. And sort, which is sort. All these primitives are available in PyFAI through code generation in a very easy and intuitive way to use. We are not using them though. So our operation, the histogramming, is a scatter operation which needs to be protected through atomic operations. But as we decided not to use those, we have to find a way to go around this. And what we did was to transform our operation from a scatter to a gather, which means, in principle, the creation of a lookup table which keeps the correspondence between the contributions and the pixels of the image stored in a table. This operation, unfortunately, requires twice the time as normal histogramming. But we chose to use this because the lookup table can be reused on several images that share the same experimental configuration. The lookup table creation is done on Python on a single thread, but there's also plans to port it on OpenCL on GPUs. So with the lookup table, our operation is transformed to a matrix, a sparse matrix vector multiplication, which can very easily parallelize, for example, through Python OpenMP. Here is a code that does a. Okay. No, you want to take over? No. I will skip the code because we don't have much time. We see the initial speed up from going from single thread to OpenMP with lookup table. It's about 2 or 3 times. And then we move on to the memory consumption of the lookup table and the precision of our problem. As you might know, most of the GPUs have limited support for double precision arithmetics, which is also displayed by. So we're forced to use float 32-bit floats, but this could result into problems when dealing with big sums, because as is displayed by that code symbol there, we have the average of a big array of ones, which is not actually one. What we did was to use Kagan summation, which is a technique of for correcting the sum. It takes 4 times the operations, but as you can see from the benchmark here, we have all the OpenCL version that uses the Kagan summation perform much better than the ones who are using OpenMP. This is more apparent in new CPUs that use bigger SIMD engines. Okay, we move on to the lookup table size issue. When doing the lookup table, we have a lot of non-useful data, which is in principle zeros, which result in big overhead on data transfer, and can even result into code failure because of insufficient memory on the device. What we did was to move on to introduce the CSR compressed sparse row format, where our data is kept in 3 arrays. One is data where the contribution is kept. One is indices where the correspondence to the appropriate pixel on the image is kept, and the row index pointer where it points to the start of each bin at the other 2 arrays. Finally, I show some benchmarks here. Finally. You can see the performance increase from lookup table to CSR, which is about factor of 2 or 3. And also, we can see on the other benchmark, which is done only on CSR with many different many core architectures, that our code performs consistently well, with the surprising fact that a very cheap consumer-grade GPU gives top performance. And so I pass Stan to Jérôme for concluding statements.
Okay, just I said that the library has a Pythonic interface, so this can be obtained by calling 4 lines, an import statement, loading the geometry from a file, loading the image, and just one single call on integrate 1D that provides the crop you obtain. So we have summarized the speedup to obtain. So from NumPy to parallel code, we have a factor 36 of speedup, and going from CPU to GPU, we have an extra factor 4 or 5. So I will conclude that PyFAI is available. It's in production on many beamlines. We have 1D and 2D regrouping available. We have multiple output space. That's for people who are interested. We have multiple pixel splitting schemes, and the calibration tool is available with a GUI that is still in preparation. Cython is a great tool. OpenMP may be a bit tricky to use sometimes, and PyOpenCL is really a great tool that provides NumPy-like object on the device. A lot of algorithm already implemented on the fly compilation, reduce hassle for initialization, and it makes really CPU look like GPUs, and you will learn a lot about how CPU works if you work with it. Finally, I'd like to acknowledge the Link Scheme 2, a European grant that pays Yannis' contract, who already paid Dimitri's and Zuber's contract. I'd like to thank my colleagues from other synchrotrons, because we are well, it's not an official collaboration, but we are working together to get a tool that we need. So Frédéric and from Soleil and Clemens from Chicago. I'd like to thank Aurore, who worked on the GUI side, Armando, who's the author of PyMCA, and Claudio. as well as all the ESRF beamlines who support the project and well, request my time to be allocated on PyFAI. And I'd like to thank you for your attention. Thanks.
So we're behind schedule, so could the next speaker just come while there is maybe one quick question?
So since your quadrature scheme is just a sparse matrix multiplication, why not pre-compute the sparse matrix and just call you know, a sparse matrix library like
yeah,
you know,
that's the one from
PyFAI
SciPy, and it gives really good performances. The problem is that yeah, some pixel may go mad from one image to the next, and the detector may mark them as dead. So we need, in addition, an extra step to check that the pixel is still valid when it's read. So we need an extra check within the sparse matrix multiplication. So this is why we don't use it. But actually, it's while doing the two multiplication, while doing one multiplication is is as fast as our code parallelized on 8 cores. So yeah, it's much faster. But we need to do this extra test to ensure that we skip out pixel that died.
Thank you again.